This is example 8 from lecture 6. We have an optimization problem. A farmer wants to maximize a profit from a crop of wheat that depends on the amount of nitrogen or fertilizer applied to the crop. We have a production function where the yield depends on the amount of nitrogen. We have the equation there. N equals nitrogen, a common fertilizer. Let's look at some of the other terms here. The use of nitrogen, the fertilizer, is in terms of pounds per acre. We have the price there per pound and pounds per acre. 1 pound, LB being the symbol for a pound, is approximately equal to 450 grams, or 2.2 pounds equals 1 kilogram. 1 acre is equal to 0.4 of a hectare. 2.5 acres, approximately equal to 1 hectare. The yield is measured in bushels of wheat. Well, a bushel is an imperial measure of volume. Here we have a standard imperial bushel from the Queensland Museum. If you look closely, you'll see the inscription. That's about 36 litres. A US bushel is slightly smaller, about 35 litres. So now we understand our units. Let's move on to the optimization problem. We have the yield, which is the quantity of wheat produced. Well, profit's going to be the quantity times the price of wheat minus the cost. We have a profit function, so revenue minus cost. We're using the ceteris paribus condition here, means all other things being equal. So we can ignore all other costs except the costs of nitrogen. That's what's changing. All the other costs are fixed costs. Revenue is the price of wheat times the quantity of wheat. Cost is the price of nitrogen times the quantity of nitrogen. We write that out and simplify, and we get our profit function. We want to maximize profit. Well, our domain is n greater than or equal to 0. Next, we'll consider the first order condition. We take the first derivative, pi prime n is equal to, well, the constant disappears, plus 1.1976 minus 0.07 times 1.5, so it'll be 0.105 n to the 0.5. Our first order condition is we'll have a stationary point when the first derivative is equal to 0. That implies that 1.1976 minus 0.105 n to the 0.5 is equal to 0. We can solve for n. We'll have n star, that'll be the square root of n star, equal to 1.1976 divided by 0.105. That means that n star is approximately equal to 130.1. We have a stationary point. We should check whether that's a maximum or a minimum. We'll do that using the second order condition. Our second order condition is this. If we evaluate the second derivative profit function at the stationary point and it's negative, then we have a local maximum. Our first derivative of the profit function is this. So the second derivative will be, well, it'll be minus 0.105 times a half. So it'll be 0.0525 n to the minus 0.5. That's our second derivative. We want to evaluate that at our stationary point. So we substitute in 130.1, and that's equal to minus 0.0046. Therefore, we have a local maximum at n equals 130.1. Can we say more than it's just a local maximum? Let's look at our second derivative. N to the minus a half will always be positive for n greater than 0. Of course, it's undefined at n equals 0. The coefficient is always negative, so the second derivative is always negative. If the second derivative is negative, we have a concave function, and that implies that profit at n equals 130.1 is a global maximum. Here we have a graph of our function, and we see it's a concave function with a global maximum at 130.1. And And that concludes Lecture 6.